Welcome. My name is Jonas Lueck. I'm a PhD student at the University of Göttingen, and this is joint work with Mariam Garba, Tom Nye, and Stefan Huckemann, who is also my PhD supervisor. Today I'm going to talk about the Wald space, information geometry for phylogenetic trees. The Wald space is a metric space where each point is a phylogenetic tree. And a phylogenetic tree is for a fixed set of species, or symbolically speaking, labels, is a tree that depicts the evolutionary relationships between those species. All right. Now, I will start with the outline of the talk. First of all, I will motivate tree spaces. Why do we need them in the first place? Then I will construct the Wald space and also introduce how the geometry is obtained. And finally, we will do some numerics in Wald space. All right. Now, phylogenetic trees are usually inferred from common genes. And there are methods that if you measure the DNA, for example here of the fish, the horse, and the elephant, you can align them in a table. It's called a multiple sequence alignment. And then there are methods to estimate the best fitting phylogenetic tree for this multiple sequence alignment. Now, measuring different pieces of DNA usually results in a different phylogenetic tree, and thus you will naturally obtain a sample of phylogenetic trees. All are proposals for the assumed to be true underlying evolutionary phylogenetic tree. Now, we want to do statistics on these samples of trees to, for example, infer the true tree, for example, by averaging. But to do statistical analysis, you need an underlying geometry of the sample space, where, first of all, the geometry should be biologically reasonable and also computationally tractable so that we can actually compute things. To this end, fix small n to be greater or equal to 3, and this is the number of species we consider in our tree. And we denote the set of labels with 1 to n. So here, for example, the fish, the horse, and the elephant would be replaced with the symbols 1, 2, and 3, say. All right. There are existing tree spaces, and perhaps the most prominent example is the BHV tree space. It consists of the rooted phylogenetic trees with the leaves 1 to n and a root 0. And the BHV space is a very, very interesting and nice space. It is a metric space, first of all, and it has very nice properties, namely one of them is that it is ket0, so globally, among others, globally of non-positive curvature, which also implies that between 2 points you have a unique shortest path connecting them. And furthermore, it's Riemann stratified, so you can imagine the BHV space to be a union of Riemannian manifolds glued together in a certain compatible way. Let's consider a small example. Let's consider these two trees, T1 and T2. They look very similar, but the labels are ordered in a different way. So these are actually different phylogenetic trees, and all edges have, for simplicity, the same edge length, the same positive edge length L. It's just a real number which is positive. Now, intuitively, what happens if we let those edge lengths go to infinity simultaneously? Well, in the limit, you would think that the information that the tree in the limit conveys for both trees, T1 and T2, is that all those labels, all those species are not related to each other anymore. So if all those edge lengths go to infinity, then you would think in the limit that those species are just not related anymore. So in the limit, in particular in the limit, those two trees would convey the same information. And from a metric space point of view, this would mean that the distance between those two trees should go to 0 as the edge lengths go to infinity. And as a limit element, you would naturally think of this disconnected forest F here. So biologically meaningful would be that the distance between those two trees goes to 0 as L goes to infinity. But for example, for the BHV space, the distance grows linearly to infinity as L goes to infinity. So this motivates construction of a new space, of a new metric space for phylogenetic trees. Let's construct the Wald space. So first of all, very roughly speaking, Wald space is just the set of all those forests with labels 1 to n. So these can be disconnected graphs where each connected component is a tree, and in total it has labels 1 to n. Now for each forest, what we can do is, for two labels u and v in a connected component, we can define the distance duv between them to be just the sum of all those edge lengths of those edges between u and v. And then what we do is we map each forest f to a strictly positive definite matrix sigma f via the following formula. The UV matrix entry is just e to the power of minus duv if u and v are connected, and 0 else. And you can think of this as some kind of correlation. So if the distance between them would be somewhat infinity, so if they would not be connected, they are 0 correlated. And if they have finite distance, then they would have correlation e to the power of minus duv. And if you let duv go to infinity, this correlation would go to 0. And if you let duv go to 0, then they would have correlation 1. So they would be the same label in some sense. Now let's denote this map with phi. So we can actually map each forest into the strictly positive definite matrices. And furthermore, under some technical assumptions, this map is actually injective. Now the question is how to define a metric on this Wald space, Wn. Let's consider the following analogy for this. We can embed the sphere into the R3, right? And then we choose very consciously the Euclidean geometry on R3, and we take the infinitesimally induced metric on the sphere, so we would obtain the spherical geometry, or also called the arc length distance on the sphere. And then we view the sphere again out of context, and we obtain a metric space. And in the same way, we do this via phi, via the embedding of the Wald space into the strictly positive definite matrices, where the strictly positive definite matrices are a Riemannian manifold, and we choose the so-called Fisher information geometry very consciously, and then we again take the infinitesimally induced metric on the subset, which we call the Wald space geometry. Then we go back via phi to the power of minus 1, so because it's injective, we can invert those elements into the Wald space again, and we obtain a metric space. This is how we obtain the geometry of the Wald space. Alright, there are some theoretical results of the Wald space. It is, for once connected, the distance between all those elements is smaller than infinity. It is a stratified space, so it is a union of manifolds glued together in some topologically compatible way. And finally, all those distances from our example before here actually go to 0. So we have this property, those distances go to 0. And furthermore, the forest, this disconnected forest, is actually contained in our space. So the limit element of this limit is actually contained in Wald space. Right. Finally, let's do some numerics in Wald space. We recently designed a path straightening algorithm for approximating geodesics in Wald space. I mean, we want to compute the distance, the newly obtained distance of our metric space, and for that we need to compute shortest paths between 2 points. Now, this path straightening algorithm takes as an input a discrete path. Let's say we have fixed endpoints f1 and f2, and let's say we have a discrete path between them already given, p1 up to pn, and the algorithm, the path straightening algorithm, iteratively improves this path by performing some kind of path straightening. Now, for the quality assessment of such a path, like how geodesic is it, we compute the energy of the path, which is using the distance in the Riemannian manifold of the strictly positive definite matrices with the Fisher information geometry, and just adding up the squared distances of the successive elements in this discrete path. Now, the smaller the energy, the better the path approximates a geodesic, and thus the shorter also the path. Right. Let's consider this example here. We have two trees, T1 and T2, and we just view a two-dimensional slice of the Wald space, which we can see here. For example, T2 is a tree of this structure, but we only see in this coordinate system here the edge lengths L6 and L7. It is actually a 7-dimensional object, but we only view these 2 dimensions here. Same goes for T1, where this is another tree structure compared to this one, and we just view this 2-dimensional slice again instead of all these 7 dimensions here. This cone point here is then this 5-dimensional tree here, and this path here, this curve that goes with straight line segments through the origin, this is the BHV geodesic. And what we did is use this as a starting path and apply our iteratively updating algorithm, our path straightening algorithm, onto this path. And you see that it actually diverges from this cone path here, and it actually converges to something that goes through a third tree structure, which is depicted here. And as another example, we started with another more sophisticated guess, and we also performed some iterations, and it seems that this was already a kind of a good guess. But just from this picture, you cannot assess the quality of those paths, but we have to look at the energy of those paths. Now here you see the energy of the BHV geodesic, which is, just to mention, not a geodesic in Wald space. The geometries are completely different. And then applying path straightening decreases the energy, which is good, which makes it more approximately a geodesic. And after 200 iterations, we have, it seems, not yet arrived at a minimum. Now, this SP algorithm is this algorithm that gives us this sophisticated guess for another starting path. And we start with a much lower energy already, and then the path straightening algorithm applied to this path also decreases the energy. And it seems that both energies go to the same level here. So as a conclusion, it seems that we can actually approximate geodesics across different tree structures. And that's my talk. Thank you very much for listening, and here are some of our recent publications to this topic. Thank you.